So here is my balanced acid redox equation. So I'm going to check my work here. I see 16 hydrogens and 6 more for a total of 22 hydrogens. And then on the product side, 11 times 2 is 22. 4 chromium, 14 oxygens plus 1 more makes 15 oxygens. Here I've got 4 and 11 for a total of 15. And I believe carbon is the last thing we have to count. 2 carbons, 2 carbons, and so all the atoms are balanced. Now let's check the total charges. So I've got a 16 positive and 2 negative 2s. So positive 16, negative 2, that's positive 12 on the reactant side, and 0 charge here and here, but 4 times 3 is a positive 12 there. So the charges are also balanced. So I've checked my work, and there is that balanced equation. This one doesn't occur in basic conditions, but real quick, if we were going to balance this as a base, just to go over the rules for that, because you may encounter those, if we change this to a base, you do it just like you do an acid. You do everything we just did, except you go in and lastly, you cancel off your H pluses. So I would add 16 OH minus, there's showing that it's a base. And then I'm going to come over here and add an equal number, 16 OH minus. So however many H pluses you have, if it is a base, again, this one's not, but I'm just showing you how to do it here. You go to your H plus side and add an equal number of hydroxide, and then jump over and add the same number on the other side. 16 H pluses and 16 OHs is 16 H2Os. So I'm now rewriting that if this were a base. And then the last step, if it's a base, is to cancel those waters again. So I've got 16 reactant side, 11 product side, so these are going to all get canceled out, and that's going to take 11 of these away, so we would have 5 H2Os. So if this did happen to occur under basic conditions, we would have 5 waters, 2, 1, 4, 2, and 16 OH minus ions on the product side. So again, if it's a base, you do it just like it's an acid, and then you fix it to make it a base later on. It's a pretty simple process for balancing acid-base redox equations. All right, so what exactly is an electrochemical cell? Well, kind of by generic terms, it's kind of a battery, if you want to think of it that way. A battery kind of starts with the basis of an electrochemical cell. And here's kind of an intro to how this works, and I want to take you through some terms that you need to be familiar with and how this ties into that reaction that we were talking about a moment ago. So we were working with an equation a moment ago where we had Zn plus 2Ag plus, I'm going to the net ionic equation. The nitrates are spectators, forming Zn plus 2Ag solid. So there's the spontaneous reaction that we came up with, and again, you can tell that that's spontaneous by using your reactivity series of your metals. It's one way. We'll learn another way here in just a moment. So here's kind of the simplistic approach to what a galvanic cell or an electrochemical cell, what it would look like. So I've got represented over here in solution, I've got my silver ions and my nitrate ions, so that's my silver nitrate solution. And if I place a piece of silver in there, I get no reaction. If you were trying to ask yourself, does that react? Does silver displace silver? Absolutely not. Nothing happens at all. On this hand, over here, I've got zinc, my solid bar of zinc here, placed into my zinc nitrate solution. Again, I got those ionized, broken apart there in solution. The pink ones are my nitrate ions over here as well. Zn++ is the blue one. And on that side, absolutely nothing happens. And the answer is, until I put all this together, absolutely nothing happens. But to put this together, we've got to somehow make a connector. We've got to make some bridges in between here. And there's some options. One, you can actually use an electrochemical cell that's got a porous disc here in the middle, and basically these two glass tubes are connected, and there's a point there that allows them to connect in the middle. To keep it even simpler, we can actually take just a piece of filter paper and soak it in an electrolyte solution, salt water, and we can actually just lay that from one container to the other. And that's known as a salt bridge. So if we put that in something like sodium chloride and water, then we establish a salt bridge. And you got to have that to make the connection between the two for this reaction to occur. So as I look at this spontaneous reaction down here at the bottom, it's going to give me a lot of pictures of what's going on inside this container. So the zinc is going to be going into ion form. So this zinc over here, and it's an electrode, we'll talk about it more specifically here in just a moment, that piece of zinc metal, it's going to break down and go into solution. Now if you take a look at that, the moment it does that, we've got this unbalanced charge. We've got an extra +2 there in solution. And to counter that, jump over to the other one here, for each zinc that does that, 2 silver ions are going to precipitate. They're going to form silver solids. So these 2 silver ions here that we have, they're going to go, and this electrode here, it's going to begin to build up. So we got the zinc electrode that's kind of breaking down, and this silver electrode whose mass is increasing. The mass is going to go up on that. And now we've got, between the two, a balance of charges. We've got 4 nitrates and 2 zinc plus 2 ions. Now again, these ions are going to migrate through this bridge as well in order to kind of maintain that charge. But there's one other key part to this. None of this happens unless we go back and we take a look at those half reactions. There's another part of this half reaction that we have to think about, and that's the fact that for all of this to happen, zinc needs to gain 2 electrons, and the two... Let me try that again. Zinc needs to produce 2 electrons, and the silver needs to gain 2 electrons. All right, so it looks something like that. And again, that's my balanced half reaction. The electrons here are going to be produced over here by the zinc. So when that zinc breaks down and goes into ion form, there's going to be 2 electrons, and we're going to send those 2 electrons over to the silver. And the way we're going to do that is we're going to connect these with a wire. And then maybe in between here we connect that wire perhaps to a light bulb. Or in a moment we'll connect it to a voltmeter. So we got the wire that's connected to this electrode, and it's connected over here to the silver electrode, and that's going to allow those electrons to flow through there. So when the electrons flow through, they go into the light bulb, they light up the light, and then they arrive at the silver electrode, which again allows those 2 silver ions for each 2 electrons to go ahead and precipitate onto the other silver metal that we have there. So again, what we get is we get this complete circle here, and in terms of a battery, from here down below, this is what's represented by a battery. And this one here that is the zinc, in this case, that's producing the electrons, we would label that with a negative because it's producing those negatives, and they're going to flow toward this side, which is a positive. So if you look on a battery, you're going to see positive and negative. As a matter of fact, this is called a cathode, and this electrode over here is called an anode. And one way to remember that is the anode is where oxidation is occurring. So here's the zinc going from 0 oxidation to a +2. So the anode is being oxidized, so anox. And what's going on at the cathode is reduction, so red cat. So anox, red cat, helps you to label those. Now again, if you can't remember that, the electrons are going to be produced at the negative electrode, the anode. That's negative because it's producing those electrons, and they're going to flow toward that positive side, the cathode. So in simplistic forms, this is kind of how a battery works. We've got the electrons heading in that direction, and to kind of maintain that whole negative part of this loop, that also means that in the salt bridge we're going to get a migration of ions, and if negatives are going to cross this way, to maintain that, we need negatives to migrate that way through the salt bridge. So we would simply label that and say the anions are going to move that way. For instance, it could be a nitrate, moving that way. Or the same thing in terms of maintaining balance. Cations could simply migrate in the opposite fashion. So be able to label which way anions go and cations go. And again, all of this starts from, can you write and balance the spontaneous reaction? Can you do the half reactions? And then if so, you can establish and draw a galvanic cell. In terms of stoichiometry, one of the things that happened was we had this decrease in mass of this anode as it breaks down and goes into ion form, and we get an increase in mass over here. So we could do some stoichiometry with the changes in mass of those, and I'll do some of those calculations in the more advanced latter parts of this video. I'm going to take you through, how we would actually calculate how many volts that battery would be. Again, single cell battery. So in order to go through calculating the volts or the electromotive force within this, I want to go over just a handful of things here. These are electrical terms. One is current, and current is our flow of electrons. And the units that we use are called amps, and an amp is actually so many coulombs of charge per second. So an amp represents so many coulombs per second. On the other hand, another word that we talk about sometimes when we're doing electricity is voltage. I used that a moment ago, and measures volts, and that's joules of energy per coulomb of charge. A few other things that I want to throw in here that you need to be familiar with. This coulomb that we talk about, that's kind of like a quantity of electrons. And when I say kind of like a quantity of electrons, 1 electron is, of course we know that electrons are negative, so I'm going to probably inadvertently leave that off later on, just knowing that they are negative, but 1.6 times 10 to the negative 19th coulombs. Now when I say I'm going to leave off a negative, the fact that the electron is negative, we just say the charge on an electron, elementary charge, is 1.6 times 10 to the negative 19. Do not leave the negative off for the negative 19. The other thing that you need to be aware of is, just a reminder, 1 mole of whatever it is we're counting, and in this case it's going to be electrons, is 6.022 times 10 to the 23rd electrons. There will be some more advanced calculations that we'll get into later on where we're going to need to know some of those things in order to solve these. But the first thing I want to get into is going back to that reaction that we had a moment ago, and that is, what would be the cell potential for our cell with zinc and silver ions. Now, in order to do that, we're going to start with solutions are 1 molar. And in order for these to be what we call standard potentials, all solutions will be 1 molar. Now, we'll talk about how we address that later on. And so we get zinc ion and 2 Ag solid. So what would we get for this? Well, I'm going to do the 2 half reactions. And now what I'm going to look up is something called standard reduction potentials. So the standard reduction potential gives us a value for the reduction process. Now the problem with that, I'm not going to find this value for a reduction potential because it's oxidation. But it's real simple. All I got to do is find the reduction value and change the sign. On the other hand, up here we've got coefficients of 2. And if you were thinking about thermochemistry for joules, when you double that value, you would double the joule value. But here's the thing. Remember, these standard potentials, these are in volts when we look them up. And it's a joule to coulomb ratio. That's what a volt is. So yes, by doubling the coefficient, we double the joules. But we also double the coulombs. It's 1 silver ion or 2 silver ions. The value is not going to change because if you double the top number and double the bottom, you still end up with the exact same ratio. So we look those values up.